Welcome back everyone to note video number 5. We are still in the physics unit, but now we're starting part 2. And in part 2, we're going to discuss the force. The force is discussed in chapter 10 of your physics book, so make sure that you go and read chapter 10. And in this chapter, you're going to learn about forces and their impacts on motion. You are going to back it up. There we go. You're going to learn about the fact that forces always come in pairs. You're going to learn about this guy, probably the most important person to discuss early on when you're learning about physics is Sir Newton. We're going to talk about gravity and momentum. And that's going to take us to the 2/3 of the way through the physics unit. So what is force? Well, a force is any push or any pull on an object. So objects tend to want to stay where they are, or they tend to want to not change what they're doing. And if you in any way try to alter the state that the object is, if it's either moving or sitting still, that would always require some type of a force, some type of a push or a pull on that object. So when we measure forces, we measure them in the units called newtons. You may remember from Unit 1 when we discussed the different SI units that Newton is one of the units that we talked about. Well, it's not a unit of length. Newton's not a unit of temperature. It's not a unit of time or mass or volume. Newton is a unit of force. Now, when we learned about it in Unit 1, though, we said that the standard unit of weight was the Newton. Well, here's the big secret. Weight is a force. So weight is the pull of the Earth's gravity on you. What you feel as that pull is what we call weight. And we can measure how much of a pull that is in the units of newtons. So you get net force, vocab term, you get net force when you combine all of the forces that are acting on an object, because you can have gravity as a force, you could have wind speed as a force, you could actually have somebody like pushing down on top of the object as a force, there's frictional forces, there's all kinds of these forces, there's air resistance that can be interacting on one object depending on what it's doing. And if you add them all together or subtract them or whatever it is that they're doing, if they're canceling each other out or if they're like combining to make bigger forces, once you have all of that and that whole picture put together, you could have one kind of arrow with a number on it, we call that a vector, that is a net force. So let's do a couple of questions here to make sure we're all on the same page. So let's say Mr. Spell gets a deer, shoots a deer, but it's huge. Well, all the deer that Mr. Spell shoots is huge. But so he needs help pulling it out of the woods. Well, he calls on Mr. Bain. It says, Mr. Bain, got a big deer. How about we go pull it out of the woods? So they each tie one rope to the deer, and they each pull with 5 newtons of force. If this was happening, how much force would be pulling on the deer? Well, in physics, it always helps to draw kind of a picture. So if we had the deer, and we have Mr. Spell, and we have Mr. Bain, and they each have a rope attached to the deer, and each rope is 5 newtons of force, and they're both pulling in the same direction, well, you would add them together, and you would get a whopping 10 newtons of force. Not tough stuff. If you have two forces and they're operating in the same direction, they combine together. FYI, we'll use arrows a lot to represent forces, and notice how the bigger number has the bigger arrow. It makes it much easier to keep them straight if you do that. Alright, so here we have Mr. Alexander and Mr. Heller. Well, they're both trying to go through the same door, but in opposite directions. Both believe the door's stuck, so they start pushing harder. Well, Mr. Alexander pushes east with 10 newtons, and Mr. Heller, holding a cup of coffee, so he can only push with 3 newtons. Well, what's going to happen here with the door? Well, if they're going in the same direction, you add them together. If they're going in opposite directions, yeah, you're going to subtract them and figure out who wins. In this case, the door is going to experience a net force of 7 newtons to the east, and it's going to swing, and poor Mr. Heller's probably going to be wearing his coffee. Here we have Jason and Michaela, and they've challenged Olivia and Nick to a tug-of-war battle. Well, Mrs. Lafayette pulls out the rope. War begins. Michaela goes beast mode and pulls west with a force of 9 newtons, while Jason tugs with a force of 6. Olivia and Nick both pull east with a force of 7 newtons. What is happening? What's the net force on this rope? Well, we have a 6 and a 9. Those would be Jason and Michaela. We have a 7 and a 7. That would be Olivia and Nick. You add them all up. These two would come together to be 15 this direction. These two would come together to be 14 that direction. And Jason and Michaela would be the 1 Newton victors. So it's not a lot of force, but it would be enough to start pulling them a little bit to their direction. Alright, so here's one that actually gets a little bit tricky. And this is what more of your high school physics ones will start to look like, because they start to involve angles instead of just going straight back and forth to each other. You don't quite have, or you don't, not quite, there's no quite to it, you don't have the trigonometry knowledge to be able to do problems with odd angles, or any angles, but there is a way around it. So we're going to show you how to work through one that uses a triangle. So anything that I ever give you will be a 90-degree triangle, and you'll be able to use this. So we got a high wind, and it blows your winter lawn ornament up into a tree. Well, when spring comes, you got to get Frosty back out of the tree. So you and a friend, you hook 2 ropes to the base. You don't want to pull straight down on it, because then it's going to fall down on your head. So you hook those ropes up, and you hook them up at angles. We'll say 90-degree angle. And you're pulling at 5 newtons each. Remember, a newton's not a lot. I keep using these low numbers of 5 newtons because it's just easier to work with small numbers. But a newton is really small. Remember, 1 newton is only about 1/4 of a pound. It's like 4 newtons to actually have a pound. Anyway, what's the net force that you're putting on Frosty? So, if we have... Oops. If we have... Where's my... There we go. If we're pulling like this, and here's our 90-degree angle, and each of those is 5 newtons. Well, the fun thing that you can do in physics, and you're going to do this a lot when you get to the high school, is once you have your little vector diagram drawn, you can move these arrows around and figure out a way that they would come together. And in this case, you could actually take this arrow and move it down here. So it would look like this. You'd still have this one, and we'll say this is this arrow. But you can actually take that orange arrow and slide it down this way and put it here. And turn that triangle into this. And then you can make your 3rd side. And that is going to be the actual combined force. And we'll show it in a different way. Come on, computer. There we go. All right, so let's let PowerPoint do the work. We have our 2 angles, or 2 lines that make the angle. And here is where one of the most useful formulas that you're going to come across is going to come into handy. And you've learned about this in math class. This is the Pythagorean theorem. And the Pythagorean theorem says that if you know the lengths of 2 sides of a triangle, then you can figure out the length of the other side of the triangle. And the ratio and the relationship is always the same, where small side squared plus small side squared equals the longest side squared. Well, if we can transplant these little arrows around, we want to figure out what the length of the red line on the triangle would be, because this is going to be the first force, the second force. This will be what we get when we combine the forces together. It's not going to be a straight like 5 plus 5 because we're not both pulling in the same direction. We're losing some of that force because it's not in the same plane. So we would get 5 newtons squared plus, or 5 square newtons I should say, plus 5 square newtons would equal the long side. So 50 newtons would equal the long side squared. and you would get 7 newtons, roughly, because 7 squared is 49. So it's going to be 7 and some change. We just rounded it off. So that means if we had a person pulling with 5 newtons of force this way and a person pulling with 5 newtons of force this way, that the actual object would experience a downward pull of exactly, well, of 7 newtons, 7 and some change. We're going to work out a few problems with triangles, and you'll get the hang of that. All right, so there's different kinds of forces. We have balanced forces. I actually had some people from Study Island came up and were asking me about this because of some Study Island questions. If you have equal forces in 2 different directions, that means they are balanced. That means your net force is 0. There's no net force in any one direction. And when this happens, you get 0 motion. An object with balanced forces won't start to move. Likewise, if there's an object that's moving and it only experiences balanced forces, it will continue to move. It won't ever stop. It'll just keep doing what it's doing. So an object with balanced forces continues to do whatever it is it's doing now. It might be sitting still, that might be moving. But if you have unbalanced forces are what you would have if you would end up with a net force in one direction or another, then you get motion, or a change in motion. So if you have an object that's sitting still and it experiences unbalanced forces, it could move. Or if it was already moving and you put unbalanced forces on it, it's going to move in a slightly different way, faster, slower, change angles, curve. There's frictional forces. Frictional forces occur when you have any 2 surfaces that kind of rub against each other. So friction always moves in the opposite direction of motion. That's really important to remember. So if an object is starting, a little chalkboard up here. If we had a table, and we put a box on the table, and we take that box and we start to push it this direction. Well, as soon as you started to push that, you would experience friction in this direction. So any direction that you're trying to move an object or that an object is moving, if its surface is touching another surface, you're going to get force in the opposite direction, and we call that friction. Without friction, objects would just keep moving. Without friction, you couldn't walk. Friction's pretty important. So the strength of the frictional force depends on 2 things. It depends on how hard the surfaces are pressed together. So the more pressure there is pushing the two surfaces together, the greater the amount of frictional force that you'll have. And in general, how rough or smooth the surfaces are will impact the friction. Mostly it's because of how much surface area is actually in contact with each other. But in general, smoother surfaces will have less friction. So, what are the 4 frictional forces? That's fun to say, 4 frictional forces. The first is static friction, and this is the strongest. So you're going to need to remember these by their level of strength. And you should definitely know that static friction is the strongest one. It's the one that's got all the muscles. So if something is not moving, that's called static. If it's stationary, it's static. So if something's not moving, it takes the most amount of frictional force that you have to overcome to get it to start moving. Sliding friction occurs after the object is already moving. So if you have one object that has a surface that's sliding against another surface, then you get sliding friction. Sliding friction is nearly always less, you can just consider it being always less than static friction. So that means, and it's a really, really, really important, the real life implication here, that if something is moving, it's easier to keep it moving than if you stop and try to get it to move again. So if you're ever like hauling things around your backyard, like dragging a big tarp full of leaves or pushing a box down the hallway or something like that, it takes more energy to get it started than it does to keep it going. Which is why if you're really struggling to move something, once you get it going, you want to try to take it as far as you can before you stop to take a break. Because it takes that much more energy to get it going again. You don't want to waste that. Rolling friction is even less than sliding friction. And rolling friction happens between two surfaces when one of the surface is rolling over the other. So not quite sliding, but rolling. You can do pretty amazing things with rolling friction. It makes, imagine trying to drag these really, really heavy blocks across the ground. It would be nearly impossible. So what the ancient Egyptians did, or what we think that they did, is that they took these logs and they would put a log in front of it and keep pulling it. And there would be a person's job that would be to grab the log and put it in the front, and grab the log and put it in the front, and grab the log and put it in the front, and just keep it going. And they wouldn't stop, because if you stopped, it was really hard to get it going again. So they just continuously drug these stones without stopping. And if you were a little slow getting that round log there in front, and you didn't get out of the way, they just kept going right over top of you. There was no stopping those blocks once they started them going. The last one is fluid friction. And fluid friction is pretty much like rolling friction, but on a microscopic level. So remember what the different states of matter are like. You have your gases, which are your molecules that have space between them, and they can fly around and bounce off each other. You have your solids, where the molecules are all really close to each other, and they're kind of stuck in place. And in between those two states, you have the liquid. Remember, in the liquid phase, the molecules are touching each other, but they have the ability to kind of tumble and roll over each other. So what fluid friction is it's like the rolling friction of you against the molecules of the liquid or the molecules of even the air. Air resistance is a type of fluid friction. So as those little tiny molecules roll over your body, that creates friction, that creates force. And it's the force that allows you to do things like skydive, or it allows you to do things like swim. It's also why when we have motors or things that have lots of moving parts, like if you could look inside of a motor, you would see these like wheels and gears and things like that are rubbing into each other. And if they were actually touching each other, they would get so hot from the friction, all of that energy would turn into heat, and the metal would literally melt and stick to each other, and your engine would, instead of it being a whole bunch of single or independent moving parts, would be one solid hunk of metal that would never move again. So to prevent that from happening, we put oil in the car. And the oil in the engine kind of coats all of those metallic pieces that are moving and touching and grinding into each other, and it creates a barrier between them, because you can't compress a liquid. So when these two pieces kind of touch each other, instead of the metal surfaces actually touching, you get the coating of oil that's touching each other, and the molecules in that can roll and slide, and it dramatically reduces the amount of friction that takes place inside all those moving parts. All right, a couple quick check questions. These are going to appear mathematical, but they're conceptual. The answer is not math. So we have John and Ben. They're moving identical boxes across the same floor. They're both currently pulling with a force of 10 newtons. We can tell that with a scale. But Ben's box is moving and John's is not. How is this possible? Think about it. Second quick check question. June is using 5 newtons of force to push a 50-pound ball across the floor. Abby's using 5 newtons of force to push a 50-pound box across the same floor. Why is June's object moving much faster than Abby's? All right. The next booby trap will have 12 questions. Good luck.